Basically, when you have a circuit, and the circuit be as complicated as you want it to be, so it could be this circuit here. You could have 3, 4 loops, 4 or 5 sources in it, whatever, and attached to some, we'll call that the load resistor, R sub L. What Thevenin says, you know what we can do? We can take this circuit that you see here, that circled one right there, and we can replace it with a voltage source, which we'll call V Thevenin, in series with a resistor called R Thevenin. And now let me put that load resistor. That's where you cut it. Like if you were to cut it right here, if you take that circuit and cut it right there, you can replace it from this point on with this one. So this box here, let me just make it red color. This box here is the equivalent of this. The question is, how do you find V Thevenin? How do you find R Thevenin? We'll get to that shortly. But that's the Thevenin equivalent. Now the Norton equivalent, it says you can take this circuit, that's the Thevenin here. The Norton says you can take this circuit, the same one, take this box, the one you see in red, and replace it with the current source, we'll call it I Norton, in parallel with R Norton. Bless you. So this is the Norton equivalent. What's inside this box, we're going to replace it with this one. And again, how do you find I Norton? How do you find R Norton? We'll get to that later. I can tell you to find V Thevenin, usually that's V open circuit, unless your circuit does not have a source in it, source free. And I Norton normally is I short circuit. R Norton is the same as R Thevenin, the way we find them. It's the same resistor. If you look at this circuit, it's really source transformation of this one, or this one source transformation of that one. So if you know one, you can do source transformation, you have the other one. But we're not going to do them that way. So let's take an example and see what we have here. Let me just go and pick a problem, maybe a good problem.
Wait, what was the V30? What is that? V Thevenin equals V what?
V open circuit. And I Norton equals I short circuit. So this is I short circuit. From the name, that means you put a wire there, right? And this is V open circuit. So let me take an example. Now I'll take one, let me see if I can get something halfway decent. I don't want it too easy. Okay. Here's an example. You want to do Thevenin first? So we'll do Thevenin first. So let's say we have this circuit. Leave a little space on the top. 1 amp, because I have to go a little bit higher than that. I have 0.8 ohm here. I have 5 ohm here. Another 5 ohm on the top. ,2 ohm. And let's pick a value for R sub L. What should we use? What do you want to use for a resistor here? Pick a number. 10? Okay. And let's say the current here, we asking, what is that current? I. What Thevenin said is we can take this circuit, cut it right there, where you see the X's. That's where we're going to cut it, and replace all of this. All this, what you see there, replace it with a voltage source, we'll call it V Thevenin, with the resistor here of R Thevenin. This is the cut right there, and this is that 10 ohm. And since this circuit is equal, this box here is equal to the other box, my current should be the same. That's supposed to be equivalent to this. So if I can find the current here by doing what? V Thevenin divided by the sum of these. Ohm's law. Not voltage division, Ohm's law. I equals V over R. So what is the equivalent of that? So let's find V open circuit. Again, that's known V open circuit. So we chop that circuit, we take that resistor out, and we're looking at this. And you can still use all the stuff that we learned before. And that's your V open circuit right there. How do we find that voltage right here? How do we find it? Well, first I can combine these two resistors into one. 5 and 5 will be what? 2.5. Maybe I'll do source transformation. Notice current source in parallel with that resistor. Do source transformation. V equals I times R. So V will be what? 1 times 0.8, which is what? 0.8 volt. That's the 0.8. That's the 2.5. And that's the 2. And this is V open circuit. Can I combine these guys into one resistor? .8, 2.5 and 0.8 is what? 3.3? And V open circuit is going to be voltage division. Is the voltage cross that resistor, the 2 ohm resistor right here. So it's going to be 0.8 times 2 over the sum of these two, which is what? 5.3. So what is V open circuit going to be? There's my calculator. F18, there we go. 1.6 divided by 5.3 equals 0.30. So I got the V open circuit, which is V Thevenin. So V Thevenin here equals V open circuit. I mentioned that early on the first page. So I know V Thevenin, now I need to find R Thevenin. How do we find R Thevenin? There's multiple ways of doing them. There's different, every book has different technique. What I found out probably one of the best methods to follow these guidelines. If your circuit, the circuit has only, like in this case, independent sources, if the circuit has only independent sources, only, R Thevenin is equal to R equivalent after you kill all the sources. Kill all this, the word kill maybe not a nice word to use, but how do you kill a source? A voltage source becomes what? When you kill it, because it has a value of 0, it becomes a short circuit. A current source, because you want to have a value of 0, if you make it a short circuit, the current source, there's current going through it, so it's not a 0. So how do you make it no current going through it? By making it what? Open circuit. So that's how if the circuit has only independent sources. If it has independent, dependent, I'll change the rule. So let's look at our circuit. It has only independent sources. That's the one we're trying now to find R Thevenin. So I'm going to kill that source, and I'm going to be looking back to see what R equivalent is. So here we go for this example. What is R Thevenin? Which is, by the way, the same as R Norton. So if you're doing the Norton equivalent, it's the same thing. R Thevenin is going to be what? Let's kill this source. Again, when you kill a current source, you make it what? Open. So it will look like this. Point 8, 5, 5, 2, and this is looking back this way. What is R equivalent, which is R Thevenin? Bless you. If I look back, what is that R? Looking back from this end. Again, I can take these two, put them together, that's what? I don't need this wire dangling there. That'll be 2.5. And again, what is that equivalent R? Notice we can combine these two guys into one. 3.3. That's a 2 here. A 2. And what is R Thevenin looking back? It's 2 in parallel with what? 3.3, which is the product over the sum. That's 6.6 over 5.3. So my R Thevenin is 6.6 divided by 5.3, 1.25. Now again, what we're going to do is take this circuit out, replace it with this. So my new circuit will have V Thevenin, which is equal to what? 0.3. R Thevenin equals what? 1.25, and we get the 10 ohms. So now the new circuit, the Thevenin equivalent, will be this one. 0.3 volts, 1.25, and we have the load resistor, which is 10. And what is that current? Well, if I combine them, it's not going to change I. So you can take that circuit and change it to this. 0.3 divided by one resistor of the value of what? 11.25. Because I'm looking for the current, not the voltage, so I can combine them. So now what is I equal to? 0.3 divided by 11.25. And that's, it looks like about 26.7 milliamp, or 0.027267. So that's how we find R Thevenin and V Thevenin when you only have independent sources. Now, if I wanted to find the Norton equivalent for the same circuit, this is a Thevenin. The Norton for the same circuit, I'm going to repeat the process, but instead of using V Thevenin, I'm going to find what? I Norton. So I'll do that again. Redo the same problem. So same problem, previous problem. Find I using Norton equivalent instead of Thevenin. So again, here's my circuit. In case we forgot, we're repeating the whole thing. The good news is half it is done. You'll see that because that resistor is the same. R Norton, R Thevenin are the same, so I will not waste your time recalculating R Norton. I'll just take the answer from 2 pages ago. Again, we're going to cut it here. So we're going to cut it right there and replace this box, what's inside the red box here, with I Norton in parallel with R Norton. Here's the good news. I'll just write it right now. R Norton is always going to be the same as R Thevenin. So we know that from the previous page, which is 1.25. We just did that. The process is the same. So how do we find I Norton? I Norton is actually I short circuit. What does that mean? That means when you take this circuit, you want to put a wire here and find the current coming down through that wire. Oh, I don't know why I made 0.8. That's a what? That's a 1, not a 0.8. My mind is one step ahead. 5, 2. And now we're going to take a wire here and put it right there. And find that current I short circuit. That's your I short circuit, right there. Well, what's going to happen to that resistor, by the way? Gone. Why? This is in parallel with 0. The equivalent of that, the product over the sum. 2 times 0, 0 divided by 2, 0. That resistor is gone. When you short circuit a resistor, might as well just take it, yank it out, throw it in the trash. So your circuit now will look like this. One, 0.8. I'll do two things in one at once. These two in parallel, that would be what? 2.5. Then this is gone. This end will go through that. And that's my I short circuit. Because that 2 ohm is gone. I can use current division here to get I short circuit. So I short circuit using current division now is your source, which is 1, times that resistor, which is 0.8, over the sum of them, which is what? So what's 0.8 divided by 3.3? The current is 0.242, roughly. That's I short circuit. Now I have the Norton equivalent. Remember, the Norton equivalent is a resistor in parallel with that current source. I know both of these. I know what that current source, I know what that resistor is. So that circuit now will turn to this. I have a current source of a value of 0.242. I have a Norton resistor, which is what? 1.25. And now this is that 10 ohm resistor. Can we find what that current is? Because that's what the question was. And we'll see the same answer when we did it with Thevenin. It was roughly about what, 27 milliamps in Thevenin? So what is I equal to? Current division. 0.242 times that resistor, 1.25, over the sum of them, this plus that, 11.25, using current division. So times 1.25 divided by 11.25. And it is 0.0269. That's roughly 26.9 milliamp. What did we get? Was it 26.9? Before? 26.7. I'm sure it's my rounding numbers, you know. But it's the same answer.
Another comment.
Huh?
Another comment.
Oh yes, I'm sure. Yep, if you carry all the digits, half the digits, it changes the answer, you know. But it makes the math really sometimes a little bit easier. Instead of doing 3-4 equations by 3 unknowns, if we do that, you know, it's not bad. The problem with this, I made the circuit really easy because your source is only independent sources. What happens when your sources are independent and dependent? For both of them. V open circuit still, V Thevenin is V open circuit. I Norton, I short circuit always. So just in summary, V Thevenin is always going to be V open circuit, always, regardless what you have in the circuit. I Norton is always going to be I short circuit. So what about R Norton, which is the same as R Thevenin? So I gave you case number one. Case number one, I said if your circuit has only independent sources, we said, what do? You kill all the sources. And find our equivalent. We said the voltage source becomes what? Summarizing here. Short. Current source becomes what? Open. That's case number one. Case number two. What about if your circuit has independent and dependent? And dependent sources. Here we don't kill anything. R Norton, which is the same as R Thevenin, will be V open circuit over I short circuit. That means you got to find both of these and divide them. And case number three, which we'll look at that too, if your circuit has only dependent sources, could be one source, could be more than one. In that one, we have to supply a source. To the circuit. I didn't say current, I didn't say voltage. We're going to add a source. We're going to come grab a source and put it in and find R Thevenin, which is the same as R Norton, by taking the voltage divided by the current. You'll get to see all these cases. We just did case number one, when you only have independent sources. Now let's look at case number two, when you have independent and dependent sources. Then we'll look at case number three, when you only have independent sources.
You mean dependent?
I mean dependent sources, yep. Thank you. So let me take an example. Here we go. Let's say we have 2.5 sine. We didn't even discuss AC yet, but it doesn't really matter what we have. We have an amplifier here, a common transistor here, NPN, you know. We have 2.5 sine. I don't know why I'm using red here. 2.5 sine, and we have a frequency of 440 T. That's your 2 pi f here. And that value in millivolts. We really don't care about that source here. We'll get to AC circuits next semester. So notice this is not a DC source, so you see a squiggly line to let you know that's an AC source because you have a sine, cosine, you know. We have a 300 ohm resistor. We have 17K resistor here. We have a 5K resistor here. And let's call this voltage, I don't know, Vx. Then we have a dependent current source right here. The top is not connected together. 0.03 times Vx. $1K. And again, let's say we have a resistor here, I don't know, we're going to use 2K. That's your load, 2K. Let's say we want to find the voltage here. What's that voltage? Bless you. What I'm going to do actually is take this circuit and cut it right there. I'm doing Thevenin again. Now I can switch it to Norton after that. It really doesn't matter when you have a dependent source, because you have to find V open circuit and I short circuit, so you can get both immediately. And I'm going to replace that with V Thevenin, R Thevenin, and that's the 2K. And if you want to do Norton, that would be I Norton, it won't be on the top. Where's the resistor going to be? Parallel. R Norton, and the 2K. Then you can answer the question they're asking us to find what that voltage is. I can use voltage division here. I can find the current through it and multiply that by 2K and get that. So this is your Norton equivalent. And this is your Thevenin equivalent. So let's find V Thevenin. Remember, when you have independent dependent sources, you need to find V open circuit and I short circuit. Because to find R Thevenin, you got to divide them. Our book doesn't do them this way, but I find out this is probably the easiest way if you memorize these rules. So let me find V Thevenin, which is V open circuit. So take this circuit, chop it right there. I don't like writing all this. Sine 440t. That's in millivolts. 300. While we at it, if I combine these resistors into one, would that change Vx? So let's do that to save some paper. Product over the sum. 5K times 17K over 22K. 5 times 17 divided by 22. 3.86K, right? This is 0.03 Vx. This is 1K. And this is your V open circuit. If you don't attach anything, leave it open. What is that voltage right here? The fact this end is open, that means there is no current coming this way. That's 0. What is the current going this way? What is that equal to? It better be the same as this. It's only one branch. Well, if it's 0.03 going this way, where is it coming from? It's coming from here. So that current is actually circling right here. It's going to make V open circuit what? Negative, not positive. It's going to mark it what? Plus on the bottom, minus on the top. So V open circuit is going to be negative 1K times 0.03 Vx. If I know what Vx is, I'm done. If I know what Vx, I'm done. Well, let's go right here. Can I find Vx? It's voltage division. It's this source, which is 2.5 sine 440t, that's in milli, times that resistor, 3.86K, divided by the sum of them. So 3.86 plus 0.3, what's that, 4.16? That's not a K, that's 300. So let's do the math. 3.86, I don't need the K's, they cancel each other out, divided by 4.16 times 2.5. Vx equals 2.32 roughly sine 440t in millivolts. So what is your V open circuit now? Negative 1K times 2.32 sine 440t. The K's and the millis, they cancel each other out. It's negative 2.32 sine 440t. That's V open circuit, which is V Thevenin.
What happened to 0.03?
0.03. I don't know. I lost it. How? I don't know. Times 0.03, yes. So we take that number times 0.03, 0.07 maybe? I forgot about it. I was too excited about Vx and the 1K, the K's and the millis cancel, I forgot the 03. 0.07 negative. Now let me find I short circuit. Now again, that's the next one. I'm leaving a space so I can draw the picture there, but I short circuit is actually I Norton. So here's my circuit again. This is 2.5 sine 440t in millivolts, 300 3.86K Vx and this is 0.03 Vx. This is the 1K. And now what you're going to do is attach a wire right here and find what that current coming down through that wire. That's your eye short circuit. Again, once you attach that to this, what's going to happen to that resistor? It's gone. So basically, I'm going to take my white out instead of redrawing that and just kill that one. Gone. It's out. So if that resistor is gone, that means the current, notice this current has to go upward. Can you see it? That current coming, there's nothing. This is gone. That means this current on the top coming in this way has to be 0.03 Vx. That's the opposite to I short circuit. So I short circuit equals negative 0.03 Vx. The good news, I already found Vx from the previous one. That didn't change. That circuit on the left did not change. Still the same three values. So I can steal that number from here and plug it in. So what's my I short circuit? Negative 0.03 times Vx. What was Vx? 2.32. Sine.
Wait, why is it negative?
Because that current's going up.
Oh, okay.
2.32 sine 440t. And the value in milli. You do your math. That's going to be a negative negative 0.03 times 2.32, negative 0.07 sine
Is it the same as the other one?
No, it's
this milli.
Oh.
So if you want to find R Thevenin, which is the same as R Norton, it is V open circuit over I short circuit. We have both of these values. This is I short circuit, and this is V open circuit. Can you see them? Both? When you divide them,
Isn't it just 1,000?
1,000, yep. Sine 440t, and this one, negative 0.07 sine 440t, but that's milli. Milli is 10 to the minus 3. It's on the bottom. That will make it equal to 1 kilo ohm. These numbers will cancel each other out. Sine will cancel 1 over a milli, which is 1K. So now we can say, okay, I got it. If you want to find what? R Thevenin, draw the circuit. Where's my page? Is that the same problem? Nope, that's the wrong one. I got both circuits here. I got this and I got that. So it's up to you which one you want to use. If you want to do the Thevenin equivalent, here's what you're going to have for Thevenin. Then you can finish it. We can replace that with the voltage source of V Thevenin, which is V open circuit, that's negative, which means really pointing down, but I use negative 0.07 sine 440t. In series with what? With the resistor of 1K, that's our Norton, our Thevenin. And there's a 2K right here. And the question was, what's that voltage? Can I find that voltage? Voltage division, V equals that source times that resistor, which is 2K, over the sum of them, which is 3K. What's negative 0.07 times 2 divided by 3? 0.46. Negative 0.047 sine 440t. You want the Norton? The Norton equivalent, this will be what? A current source, and we have that value, it's in milli. Where was that value for it?
Same number, just milli.
Same number, just milli? Negative 0.07 sine 440t in milliamp with 1K here. $2K. You want to find that voltage. Well, we can find the current through that. We'll call it I sub 2 first. Should be the same answer. I sub 2 is going to be current division. Negative 0.07 sine 440t milli times this resistor, which is 1K, over the sum of them, which is 3K. .07 divided by 3, negative 0.023 sine 440t milliamp. Can we get the voltage? Isn't that 2K times I sub 2? That's negative 0.046 sine 440t volts. Notice almost the same answer. I'm sure my rounding here is the problem. But regardless if I do it current division, voltage division, it's the same thing. By the way, if I ask you what's the power absorbed by that resistor?
Times by I.
Well, you know V and you know I, right? The power absorbed by the 2K resistor is what? It's the voltage times I. You know both of them, right there. Sure. The voltage is negative 0.046 times the sign. We'll leave the sign alone. And the current is what? Negative 0.023. Sine times sine will make it what? Sine squared 440t. One is milli, one is not, so there's a milli. What's a negative times a negative? Is it positive? 0.046 times 0.023, 001. positive, means absorbed plus, that's taken, sine squared 440 T milliwatts. That's the average power absorbed by that resistor. You tell me what time, and I'll tell you what the power. I'll tell you what the instantaneous power. Power is voltage times current. I shouldn't use the word average. We'll talk about that later, actually, average power. But that's how we handle when you have independent and dependent sources. Gotta figure out where the beginning of the problem, where the end of it. Here we go. What about if your circuit has only dependent sources? We have time to squeeze one in. And if you remember my summary here, I said if you only have dependent sources, we are going to supply a source to the circuit. And you can add any source, either current or voltage, any value that you want. Because we do a ratio. And the ratio is not going to change. So let's look at case 3 where you only have dependent sources. So this is only dependent sources. The good news about that V open circuit is 0, I short circuit is 0. You're only going to be able to find R equivalent. So let me take a circuit. Let's see if I can get one. If not, I'll make one. Okay. I don't see one here in our book, but I'll make my own. Wow. Maybe I'm blind, but honestly I don't see anything. Trying to get them at the end of the chapter looking for problems. I don't see one, so I'll make one. How about we have this circuit? We have a voltage source here. We'll say plus on the top, minus on the bottom. 2 times I sub x. Going through 5K. Then another 1K. And 4K and 1K. I just chopped it there, and there's other stuff to that circuit. I'm just taking this from a different problem. So the circuit is already chopped. So there's more stuff there, but I want to find the Thevenin equivalent of this circuit. Circuit might have more stuff to it. So you know what? Let me simplify this piece of the problem. So if I take this and try to simplify it, notice I only have dependent sources. So there is no V open circuit, there is no I short circuit for this. There's 0 and 0. So the only thing I need to do is find R Thevenin or R Norton, whatever you're trying to use. It's the same thing. Now, I sub x, I'm sorry, that's this current. I forgot, I got excited there. I'm actually taking numbers from 2 problems. So it could be ugly at the end. So what my technique says here, the one I summarized, is when you only have dependent sources, we need to apply or supply a source to the circuit. And so we're going to add either a voltage or a current source on this end. And since that's in parallel, it makes sense to add a current source. Why? Because I can use color source transformation and make my problem easier. But you don't have to put a current source. You can put a voltage source. You can give it any number you want to. So I'm going to put a current source with a value of 1. If I put a current source with the value of 1, I need to find the voltage right here. Because the ratio of the voltage to the current, it should be R equivalent.
Would you be able to use mesh to solve this?
I could. Combine these into one. Color loops there. You know the answer to this? Right? Absolutely. You want to do it with mesh? I'll do it with mesh. You could also put a voltage source here. If you put a voltage source here, then you want to find the current going through it. V over I gives you actually what you're looking for. Let's call it Vy so it doesn't look like a volt here. So that's a 1 amp current source. I'm putting a 1 amp. I need to find that voltage. So R Thevenin here, which is the same as R Norton, is the voltage Vy divided by the current, which is 1. I could have used 10. I could have used 20. It won't change anything, the value. Notice I can combine these guys into one resistor.
Okay.
And if I combine these two resistors together, that does not change I sub x, right? That's 6K. 1 times 4 is 4. That's 0.8 we said. And Vy is the voltage right here. And I sub x is this. You said you want to use mesh analysis, right? I have no problem with it.
Possible.
Yep, sure. Assign two currents. This will be what? I sub x. That's the same as this one. Assign current here. That will be what?
I sub 2.
Try again. It's not. There is I sub 2, Sam, but if using that, you have two equations by two unknowns.
Negative 1.
-1. That eliminates one equation out. Gone. That's the opposite to this. So if I do a KVL here, I'll go sum of the voltage in a closed loop is 0. Minus to plus, that's a minus. 2 times I sub x. Plus the voltage drop here because you're going to the right, right? 6 times I sub x, or 6K times I sub x. You know what? I should never use K's. I was just playing with the numbers. Because that would be silly adding K's to a normal one. I can do one of two things. I can put a K here. Because it's going to have K's, this doesn't have K. To add 6,000, take away 2 from it will be silly. You know? I just made this, so I'll make it a K here. So when you're adding, at least it makes sense there. And now we're going down here, traveling this way. So what's the current down? That'll be plus 0.8K times the current coming down, which is what? I sub x minus, and what's that current?
-1.
So that makes a plus 1. I adjusted the problem. I put a K in it here. So everyone has a K in it, so I can get rid of the K. Otherwise, my numbers will look really silly. I'm dividing by 1,000, every one of them. So negative 2 I sub x plus 6 I sub x plus 0.8 I sub x plus or equals negative 0.8. .8 times I sub x equals negative what? 0.8. What is I sub x?
1 over 6. -1%.
Yep. it's negative 0.17, which is 1/6. Well, I don't need I sub x, I need the voltage Vy. Well, Vy is the voltage cross that 0.8K in parallel. That's the voltage right here. So Vy is going to be, since I wanted plus on the top, minus on the bottom, is 0.8K times the current down, which is I sub x minus a minus, that's plus 1. 0.8K times negative 0.17 plus 1. Is that 8.3?
Yes.
0.664K, which is 664 volts. So can we find R Thevenin, which is the same as R Norton?
Yeah.
It's 664 divided by 1, which is 664 ohms. So we can replace all of this box with one resistor of 664 ohms. And whatever comes after the rest of the circuit, just attach it to it. Again, sometimes what happens is you have more attached to that circuit. You might have a piece on this end. You have a piece on that end. You can say, you know what, I'm just going to simplify the circuit. Just take that piece out and replace it with 664 ohms. Now bring in that whatever you're attaching on this end, bring in whatever you have attached on that end, and solve the newer one. Yes?
When we, after we get that 664 ohms, do we have to leave the source that we made up in the circuit?
No. The equivalent of this is just that. Again, there's more to that circuit. As I said, that circuit might have something like this on this end. There's other stuff attached to it. That's the one we just chopped here. And it might even have something attached to it on that end. Could be. So what I'm going to do now, replace all of this, that's the piece we found the equivalent to it, with what? 664. So that circuit on this end still there. Put one resistor of 664 ohm here, and attach the other half of the circuit, whatever you have attached on that end back there.
Is that always in parallel with the other two circuits?
Well, that's the equivalent of that. Yep. So we chopped this right here, and that's what the equivalent is right there when we chopped. Okay, what's the equivalent of that? Or it could be just one half of the circuit there. You might not have this part, just that piece there. Then you can put that piece. Or maybe you don't have that piece, just this piece, and you can put that piece there. So, but anytime you have only dependent sources, your supply source could be a voltage source, could be a current source. If you put a voltage source, then you find the current going through it. When you divide them, V over I, it's R. If you put a current source, you find the voltage cross that what we did here. Again, there's nothing wrong of saying, you know what, I want to put a 1 volt source here. Then I need to find the current going through it. If I make it plus to minus, that means there's current going up. Find that current, and V divided by that I will be actually your R equivalent. Your answer is not going to change. So that's how I approach these problems. I look and see what my circuit has in it. If it has independent sources only, kill them all, find R equivalent. If it has independent and dependent, I do a V open circuit, I short circuit, and divide them. If I have only dependent sources, I actually supply a source to the circuit, and find the ratio of V over I.